Mr. Bainey, and we're going to take a look at, hey, what's up, Math 1? We're going to take, hello, this is Mr. Bainey. Let's take a look at lesson 16.3, representing and describing transformations. In the last two lessons, we just looked at an intro to geometry, looking at specifically segments and angles and lots of definitions. Also, we're going to be using the distance formula, possibly the midpoint formula in this lesson, but we're going to extend that to transformations, which hopefully is something that you saw last year. And transformations is when we take any figure and we change it in some way. And so the common transformations you might have learned last year include translations, reflections, and rotations. So let's go back and review some just basic ideas, basic concept of transformation. It is, remember, changing a figure in some way, and the figure we start with is called the pre-image, and then it becomes the image, kind of like taking a picture of something. So the image is what we end up with, and the way we label transformations or points in transformations is that the pre-image, if the name of the point is letter A, capital letter A, then the image is going to have this apostrophe looking thing. We call this A prime. And it says it right up here above that diagram, A prime. So if you have point B, then the image is B prime, and so on. Okay, coordinate notation is something that looks like this. Coordinate notation tells us where to start with our pre-image. That's always going to be x comma y, and then the image is, okay, what are we doing to the pre-image to get our image? So just to show you the just what's going on with this specific rule is that we're going to take x and we're going to subtract 4. So x becomes x minus 4. So we have 0 here in point A, 0 minus 4, which means our image is going to be negative 4. And similarly, the y becomes y minus 3. So the 4 in point A becomes 4 minus 3, and that is 1. The part A, B, and C, you'll see on the next page, are good examples to go through and actually graph them and see how just the basic transformations work. I'm not going to go through those since we have quite a few examples that we'll need to get through. At the top of page 803, we're going to be looking at rigid motions. You'll want to be familiar with non-rigid motion as well, but rigid motions are defined by these properties. So rigid just means when we do a transformation on something, it's going to keep the same length of all the sides. It's going to keep the same measure of all the angles in the shape, among other things. So we have also between this collinearity, parallelism. So those are the things that they stay the same. So when it says preserve distance, preserve angle measure, and so on, it's staying the same. So if I take a shape and I make it bigger, right, the measure of the side lengths are changing, so that's not rigid. So you'll want to understand rigid versus non-rigid motion. Very, very important as we go through our the rest of our book, actually. On page 805, let's do one of these together, and then I'd like you to try the next one. So directions here say, use coordinate notation to write the rule that maps each pre-image to its image. So it's just writing the rule that's going from the pre-image to the image, then identify the transformation and confirm that it preserves length and angle measure. So we want to confirm that the side lengths stay the same and the angle measures also stay the same. So what we'll want to do is figure out -4, +4. How does that become +4, -4? And in part E, if you come up with some theory or conjecture as to what's really going on, then see if that works out for 2, 4 and -2, -4. So again, think about what is going on, and what might be a little easier is if we actually just look at the x's. So we're going from -4 to 4, right? So -4 becomes 4. 2 becomes -2, and -4 becomes 4. Well, it looks like it's just changing signs, right? So when we're writing our rule, we start with x comma y all the time. Then if the x is changing signs, that means it's going from x to -x. And let's see if the same thing is going on with our y's. So it goes from 4 to -4, 4 to -4, 1 to -1. So it does look like the same exact thing is happening for the y, so I'm going to put -y. Well, here are my my two figures, right? Remember that this is the pre-image. So I'll call that the pre-image, and this here is the image. We want to first figure out what type of transformation this is. I'm not worried about this right now since the next few lessons, in fact, actually the next module, we're going to be looking more closely at translation, reflection, and rotation. So don't worry about this part so much. If you know what type of transformation it is, cool. But we're going to skip over that actually. So does it preserve length? Meaning, is DE equal to D prime E prime? Are those equal? And it looks like they are. The nice thing here, if I tell you to find the distance of DE, you don't have to use distance formula. And some of you might. You might do it because you'll probably forget this. You can just count. It's just going straight across. So I just go 1, 2, 3, 4, 5, 6. So DE is 6. And if I go here to D prime and E prime, that's 1, 2, 3, 4, 5, 6. And those two are equal. The same thing with DF and D prime, F prime. That's 3 long this way, and then also 3. So those are both equal. What we don't know for sure is the EF and also E prime, F prime. So I'm going to do this one separately. Right, so E is, I'm going to use distance formula. And if you know how to do this a different way, go ahead and do it that way. So using distance formula, when I subtract the x's, it becomes -4 minus 2, right? X minus x squared, and 1 minus 4 squared. Okay, I'm going to do a couple steps here. So if I subtract 4 minus 2, that's -6, and I square it, that's 36. And then the next set of parentheses, 1 minus 4 is -3, squared is a +9. This gives me the square root of 45. Okay, and I'm going to do it up here. I don't have a whole lot of space. E prime, F prime. E prime, let's write down these points. This is -2, -4, and 4 comma negative 1. So I'm just going to do this mentally. If I take the x's and subtract them, negative 2 minus 4 is negative 6. Square that is 36. Negative 4 minus negative 1 is negative 3. Square that and that's 9. So I do get 36 plus 9, which is the square root of 45. So that means that EF is equal to E prime F prime. And that means that preserves length. It does. So I'll just check that off. Now, angle measure. I don't have one handy right now at this moment, but use a protractor. You'll want to at least be able to measure the angles. We don't have anything right now where we can mathematically come up with to measure these angles. So use a protractor to confirm that it does in fact preserve angle measure, and it does here in number 5. So just trust me on that. I do want you to try number 6, see if you can come up with the rule, and then prove that it does preserve length. And if you have a protractor, then angle measure. Okay, go ahead and pause it and take a few minutes to try number 6. And here's my solutions for number 6. I underlined the x's going from the pre-image to the image just to try to figure out what was going on. It looks like it was adding 1 each time. So that plus 1 is that. 2 plus 1 is 3. Negative 2 plus 1 is negative 1. And with the y's, I figured out that it was subtracting 2. So xy goes to x plus 1 and y minus 2. I confirmed through my work here. I used some distance formula to show that the side lengths are preserved. So I got those two are equal. I've got these two are equal, and these two are equal. I did skip, quite a bit of steps when I was showing my work. So it's okay if you do the same, but just know what's going on, know how to use that distance formula, and be accurate with it. And also, I didn't show it here, but you can use a protractor to confirm that the angles are all the same. So the measure of angle S should be the same as the measure of angle S prime, and so on with the other 2 pairs of angles. And we'll end off on the last page of our notes here, page 807. We're going to use coordinate notation to write the rule, just like with the last couple examples, and then we're going to confirm that it's not a rigid motion. And if we just show that, 2 of the sides that are supposed to be the same, if they're not the same, then it's not rigid. It's not a rigid motion. So here we go. Number 8. So we want to figure out how do we get from 2 to 3, from 4 to 6, and from 2 to 3 in the same rule. So 2 to 3, that could either be adding 1 or it could be multiplying by something. 4 to 6. So it can't be adding 1 because if we add 1 to this, we get that. But if we add 1 to 4, we don't get 6. So that's not the rule. And then finally from 2 to 3. So it looks like we're going to be multiplying in this case. To figure out what we multiply by, we just take our answer, right, our image, and divide it by the one before, by the pre-image. So it looks like we're going to be multiplying by 2/3. Okay, that's just 3 divided by 2 would be 3/2. I have that wrong. So times 3/2, and you can double check, 2 times 3/2 is that, 4 times 3/2 is 6, 2 times 3/2 is 3. And then with our y coordinates, look at how we go from, looks like about the same numbers. I'm going from 2 to 3, from 2 to 3, and from -4 to -6. So it's doing the same exact thing. Our rule is x comma y transforms to 3/2 x and 3/2 y times y. It's okay if you do 1.5, that works also since it's not repeating. So feel free to do 1.5x, 1.5y. Now, let's just look at a pair of sides. So AB and A prime, B prime, they're not going to have the same measure or side length measure. So A to B means we're going to do subtract the x's for A and B. So I'm doing 2 minus 4, and then 2 minus 2 here. So this is going to be 2 minus 4 squared. Here I'm going back to showing my work again, and 2 minus 2 squared. So that gives me just 4, I guess, because this whole thing is 0, right? 2 minus 2 squared, that whole thing's 0. This is going to be -2, and then squared will give me a +4. And you should know square root of 4 is 2. And for A prime, B prime, same deal here, 3 minus 6, right? That's the x's. And then add that with 3 minus 3, which that gives us 0. So 3 minus 6 is -3. That's the square root of 9, which is 3. So that means not a rigid motion. That's what that proves for us. And try number 9. Go and pause it. And here's a solution for number 9. As you can see, I off to the side here in red figured out that for the x we're multiplying by a half, right? Dividing by 2, same thing here. And then for the y coordinates, multiplying by 3 to get from the pre-image to the image. Here's my rule and my work showing that RS is not the same as R prime S prime. Their lengths are right here, square root of 37 compared to square root of 18. Okay, so not a rigid motion. That's what that helps us prove. And that's going to be it for this lesson. So in here, I didn't really go through an example of it, but know how to use coordinate rules to do a transformation, and then also know how to come up with the coordinate rule, as well as showing that it is a rigid motion or not. Okay, thanks for watching. Have a great day.